Okay, so this data preprocessing is the continuation of the previous section. So we already learned the data cleaning and the data integration. I didn't discuss how to do the data cleaning and data integration in RapidMiner, but hopefully you can try some functions, or yeah, maybe after Chusok there will be some more examples how to deal with the data cleaning and data integration. Okay, so now I will like to explain about the data reduction and data transformation in this PowerPoint. First, about the data reduction. What is data reduction? Okay. Data reduction means, yeah, you can see from the word reduction, we want to reduce. If we have a lot of data, we want to make it smaller. Okay. So the idea of the data reduction is to obtain a reduced representation of the data set that is much smaller in volume, but yet produce the same or almost the same analytical results. Because we know that when you have a lot of data, or we can say like big data, yeah, there will be many issues. For example, your computer. If your computer is not good, yeah, you cannot do the analysis. The second is the tool. If your tool is not very high computing tool, is also it will not be able to get the result. Yeah. So why the data reduction? Yeah, because a database or data warehouse may store terabytes of data. Maybe it's not terabytes now, but it's like zettabyte or petabytes. There's a lot of data. Okay. So complex data analysis may take a very long time to run on a complete data set. So if we want to run the analysis, we need to select the proper attributes or the proper features. So there are three different strategies for the reduction. Okay. The first is dimensionality reduction. What is the meaning by dimensionality? If you still remember, a column. Okay. When we learn about the object, okay, the data type, we learn that the attribute, yeah, it can be called as variable, it can be called as feature, it can be called as dimension. Okay, when we want to reduce the dimension, or if we want to reduce the feature, it means, yeah, we want to remove unimportant features. There are some ways like Wavelet Transform, okay, principal component analysis, or feature subset selection, or feature creation. Okay, so those three are the strategies that we are going to learn. Okay. So you can see from this figure, okay, let's say we have like 3 columns, 1, 2, 3, 4, 5, 6. Okay, we have 6 columns, and we want to reduce it into 4. 1, 2, 3, 4. So we can say this is the dimensionality reduction. The other strategies as is mentioned as numerosity reduction, or we call this is data reduction or instant selection. Do you still remember what is instance? Instance. It means the what are the other names of instance? Anybody? Nobody? Instance, what is instance? Row, okay, that's good. And then what are the other name of instance? We can say this is tuple, okay, that's good. What we can say for instance? Object, okay. So yeah, you need to understand that one. Okay, sample, okay, that's good. Okay, so yeah, those kind of words are the same. Okay, and yeah, you need to have the sense of this keyword. Okay, when you are dealing with this kind of data mining, data, okay, is also one of the keyword for this one, because the data means the row, okay, and I want to reduce it. So if I have a lot of data, let's say I have 5 data, I want to reduce it into 3. For example, if you have 1 million data, then yeah, I can reduce it into 1,000. Okay, so those kind of things, yeah, it can be in the data reduction. For the numerosity reduction, we can use regression or log linear models. We can use histogram, clustering, and sampling, or we can use the data cube aggregation. So we will learn those things. Okay? And the other strategies is data compression. So data compression, there are many strategies. For example, the discretization. So we compress this data. There are a lot. So we have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have the data 10. So we can make the category into 2, for example. So the left and the right. And then we can split this one. So it means the top, middle, bottom, top, middle, bottom. So we can reduce the data by compressing the data into the categorical data. So there are many other things, but this is the big idea of the data reduction. So first, let's deal with the dimensionality reduction. Okay. What does it mean by dimensionality reduction? There's a word, curse of dimensionality. What does it mean by curse of dimensionality? It is when the dimensionality increase, the data becomes increasingly sparse. Do you know sparse? So when the data have a lot of columns, you will have some not understandable data. Okay, so let me show you the other kind of example. So I have one extreme data. If you take a look on the data set that I gave to you, there is a school scores. Okay, so you can open it with your Excel, because this file is actually correlated with the Excel. So this is the data about the scores in school in America. Okay, and you can see that it is based on the year, and it has the state name Alabama, and this is the total math. Okay, this is the total math, total test takers, total verbal, the academic subject. Okay, it is related to the music, and this is about the years, and this is about the GPA, is about the years, and so on. And if you see, there are too many columns. Okay, so I give you one extreme data set, so you can try to understand what is the meaning by curse of dimensionality. We have all those columns, but will we use all the columns for our analysis? Of course, it is too complex. Okay, that's why when we are dealing with this dimensionality reduction, when the data becomes increasingly sparse, the result of your mining will not be accurate. The mining result is not in a good quality. Okay, so the thing later is about the density and the distance between points. Okay, so we will learn about this one. So it is critical for one data mining approach, which is clustering outlier analysis. It will become less meaningful when the dimensions are a lot. Okay, so we can the possible combination of subspace will grow exponentially, because if you have a lot of data like what you already saw before, okay, so the subspace, when you like try to find the correlation, I want to know the correlation of this and this, I want to know the correlation between this column and this column. So you can see how many combinations that we have. Okay, so it will consume a lot of time. And the dimensional reduction is one of the way to avoid the curse of dimensionality. Okay. And it helps to eliminate the irrelevant features, and it helps to reduce noise. It can reduce the time and space required in data mining, and it allows easier visualization. Okay. And when you do with the dimensionality reduction techniques, we have like wavelet transform, or principal component analysis, or feature selection. So you can see here, if we have only one dimension, it is easy to see the data. If you have two dimension, okay, it is easy. If you have three dimension, okay, it's a little bit complex. How if you have 4 dimensions? If you have 5 dimensions? If you have 10 dimensions? Our eyes cannot see immediately the patterns. So the visualization also cannot work properly. So that's why the data reduction is one of the approach in the data mining before you do the analysis. There's one transformation named Wavelet Transformation, or people call it the discrete wavelet transform. And it is a method for the linear signal processing or the multi-resolution analysis. So we have the compressed approximation. So this is only to compress the data, and we are trying to use the approximation. Approximation is like we cannot have a certain value, just a value that close to that value. Okay, so it starts only a small fraction of the strongest of the wavelet coefficient. So the method is this one. Okay, we have the length. It must be an integer power of 2. And then each transform has 2 functions. We have smoothing and difference. And it applies to pairs of data, resulting in 2 sets of data with L divided by 2. And it applies 2 functions recursively until it reaches the desired length. Okay, what does it mean by this one? Maybe you have difficulties to understand the method. Let's see the example. Okay, so we have a wavelet decomposition problem. Okay. So the wavelet means it is a math tool for space efficient, and we are going to use the hierarchical decomposition of function. Let's say I have S is a kind of value or a tuple, and we have the value is 2, 2, 0, 2, 3, 5, 4, 4. And after we transform with the wavelet decomposition, so this is the result of the coefficient of the wavelet. 2, yeah, 3 divided by 4 minus 1, 1 divided by 4, half, 0, 0, minus 1, minus 1, 0. So with this kind of weight, or with this kind of coefficient, yeah, we can convert later this number into smaller number with this coefficient. Yeah. So the word compression means many small details coefficient can be replaced by 0, and only the significant coefficient are retained. For example, here, so some coefficients are 0. So we may think that when we calculate the values with this coefficient, yeah, we can reduce the size. For example, we have this image. Okay, if you have this image and then you want to reduce the size because maybe it is too big, so you can like split into 2, and then first you can split into 4, and then after you split into 4, you can have the compressed file. Okay, so this is the first compressed file, this is the second compressed file. Okay, maybe the size are equal, and then after we have this one, we can compress again to the smaller one. Maybe we can create another smaller into this one. Okay. So the idea is like this one. If we have the bigger size, we make it length divided by 2, divided by 2, divided by 2. Okay. So let's say if it is the resolution is 8, so we have 2, 2, 0, 2, 3, 5, 4, 4. And then when we divide the length into 2, we want to make the length as 4. And again, we want to divide by 2. We want to make the length equals to 2. And we want to go until 1. And after we have the 1, we will use this coefficient 2, 3 divided by 4. And then 1 minus 1, 1 divided by 4. And then half, 0. And then 0 minus 1 minus 1 and 0. And we put this one into this coefficient. Let's see. We have this number 22023544, and it can be transformed to this coefficient. We have 2 and 2. So this is the resolution when the resolution equals to 8, and we want to reduce it into 4. Okay. So how we can get this number? So this number will be obtained from 2 plus 2 divided by 2. What is 2 plus 2? Yeah, this is the first number and this is the second number. This 2 plus this number and divided by 2. And the result will be here. What about this number? This number is from 0 plus 2 divided by 2. And we place this into this cell. And what about this number 4? Yeah, we take the other two cells, 3 plus 5, and then divided by 2. So we put in this cell. And then the remaining part is 4. It is from the 4 plus 4, and we want to divide it by 2, and we put the value here. Okay. After we have this one, we want to get also the residual. Okay, so in this case, we have the averages, and then we have the detail coefficients. What is the meaning by the detail coefficients? The detail coefficient is the subtraction. For this 0 is from the 2 minus 2 divided by 2. So the value is 0 and we put here. What about minus 1? Yeah, we have this 0 minus 2 and we get minus 2 divided by 2. So the result is here. What about the minus 1? Yeah, it is from the 3 and 5. We minus and then divided by 2. So we get the value here. And the last one, 4 minus by 4 divided by 2. And we got the value here. Okay. So this is when the resolution equals to 4. What about if we want to do the resolution equals to 2? Yeah, it has the same function. So we repeat again. So 2 plus 1 divided by 2, and this is the result. And 4 plus 4 divided by 2, then this is the result. For this one, we have 2 minus 1. Yeah, 2 minus 1 divided by 2, then this is the result. And for this one, 4 minus 4 divided by 2, and 0 is the result. What about if the resolution is 1? Yeah, again, we can do this one. 1.5 plus 4 divided by 2. So this is the result. And the detail coefficient will be 1.5 minus 4 divided by 2. And this is the result. So the detail coefficient will be this one. And go to minus 1 divided by 4. And then go to half, go to 0. And then 0, 1, minus 1, minus 1, and 0. So you can see this number. So that's the way the wavelet coefficient work for the data reduction. And in this case, we just get the coefficient. So this is the coefficient. And if you want to get the reduction, yeah, this is the simple reduction techniques. And we can get the Haar wavelet coefficients like this one. So it means now we can make the tree. Okay. So this is based on what we already saw before. So we have the value 2, 2, 0, 2, 3, 5, 4, and 4. Okay. 2, 2, 0, 2, 3, 5, 4, 4. And then when we make this kind of tree, if you reduce, so if you reduce into resolution 4, then we can get the detail coefficient this one, and this one, and this one. If you reduce into 2, then we can get the detail coefficient this one and this one. If we reduce into 1, then we will get the detail coefficient as this one. And this will be the value when we have the resolution 1. Okay. The other approach is called as principal component analysis. Okay. I cannot explain the details because it requires the mathematical equation and etc. But I think you can just use this principal component analysis, and it also has the function in rapid minor. The idea is to find a projection that captures the largest amount of variation in data. And the original data are projected onto a much smaller space, and it results in dimensionality reduction. And this has n data and data factors from n dimension. Okay, so it means we have like column, okay, and we have n dimension, and we have n data. Okay. And we need to find k. K is smaller than n, or smaller or equal than n, or we call this is the orthogonal factors or principal components that can be used to represent the data. Okay. And it works for numerical data only. Maybe, for example, this is the original data set, but when you convert those data, and it will be like this one, so we can have this is the principal component number 1, and this is the principal component number 2. Okay, let's see with the rapid minor. I think I will use the iris data set. So in rapid minor, we have PCA. Okay, I think we don't have the wavelet. So let's just use the PCA to handle this one. You can check PCA. Okay, so we have the fit by PCA, or we can do with the dimensionality reduction. So there are some other approaches like PCA with kernel or singular value decomposition, SVD. So let's use the PCA, and I can use the multiply. Okay, so multiply means I can do multiplication of the data. Okay. Oh, it seems there's an error here. Regular attributes must be of type numeric. Do you remember what is the problem? This one. If you take a look on this, the principal component analysis works for numerical data only. Okay, and what data we have here? Our data has the species. We have the categorical data. Then what we can do is we can select attribute. Okay, before we do the PCA, we go to select attribute and then go to PCA. What is the inside select attributes? Yeah, we can select subset. Okay. And when you select the subset, you can select the attributes. You can select only the numerical attributes. Then the error will disappear. And if you run, so the PCA will give you two principal components, the principal component of 1 and the principal component of 2. Okay, so here okay, in this case, the attributes that we have, there are 4. Okay, we have one petal length, petal width, sepal length, and sepal width. So we have 4 attributes. Okay. And using the PCA, we want to reduce. I do not want to use all the attributes. It's a lot. And with the PCA, it reduces into 2 components. Okay. So that's why this result shows only PC1 and PC2. PC means the principal component. Okay. So PC means principal component. We have the PC1 and PC2. So this is the principal component of the feature 1 and the feature 2. And if you take a look on the visualization, so So this is the result of the PCA. Okay. So if you take a look on this data, PC2 and PC1, and if you take a look on the okay, this is the properties of this PCA. Wait a moment. Oh, I think I need to. Okay, let me just show. Okay, let me correct this one, and then let me do one more time. Okay, so if I want to read CSV, okay, if I want to plot this with the scatter, okay, and if you take a look on this correlation matrix, oh sorry, maybe I need to go to the chi-square. Okay, so in the chi-square, you see that what are the most important attributes? Yeah, the highest correlation shows that petal length and petal width, they are showing a high chi-square values. Then if I want to see the result here, I can select the petal length and the petal width instead of sepal length. Oops. Oh, no. Okay, so this is the petal width information. Okay. You can use, this is the petal width, so I will use the petal length. Okay, and you can see here, yeah, the data is like already clustered with this section. Maybe I can use the color based on the species. Okay, so you can see the setosa is in the left lower part, and then the versicolor is in the middle, and then virginica is in the top right. Okay, and when we use the PCA, okay, when we do the visualization, okay, so it seems that yeah, we can like separate the left, middle, and right. Okay, even though the low or the high cannot be distinguished very well, but at least we can see some principal components to distinguish, to represent the original data. Okay, so we can just use these two features instead of using of 4 features for our analysis. Okay, that's the meaning by the dimensionality reduction with the principal component analysis. Attribute subset selection. So this is another way to reduce dimensionality of the data. Let's say I have redundant attributes. Okay, so we already learned in the previous PowerPoint, there are some redundant attributes. How can we know that it is redundant? Okay, so first, yeah, we need to find the correlation, or we can check the covariance. Okay. In this case, I would like to show you a very simple example. We can see the duplicate data. Okay, so the duplicate match or all of the information contained in one or more other attributes. Let's say the purchase price of a product and the amount of sales tax paid. I have the product 1 and the price is 1,000. I have the product 2 and the price is 2,000. And we know that there will be some tax. Okay, tax, maybe the tax is 10%. Then we have 100 for the tax and 200 for the tax, and the price is this one. If you use the price and the tax, okay, actually, yeah, you don't need to use those two. We can just use this price. Okay, it means we can reduce the dimension of the data. We can reduce these two columns, and we can just use only the price and tax data for our analysis, because they are highly correlated, or they are highly uh, redundant. Okay, we call this is redundant, because the 1000 plus 100 equals to 1100. 2000 plus 200 equals to 2200. So yeah, it is redundant. And some of the attributes are irrelevant. It contains no information that is useful for the data mining task at hand. For example, I want to know how many person who got a good grade in particular courses. Okay. Or for example, I want to predict someone's GPA. If you want to predict the GPA, yeah, I do not need the student ID. Okay. Because this is irrelevant for predicting the grade. If I want to predict the GPA, I need to only find the grade, or maybe if we have the information about gender, okay, and maybe I need to have the information about the exam score and etc. So I can try to predict the GPA, but the student ID is irrelevant, so we can remove this one. Yeah, this is what we call as the attribute subset selection. Or there are other way, we call it heuristic search. So in the heuristic search, we will select the attribute combination. Okay. So this, for example, I have 2 power of d. Okay. 2 power of d possible attribute combination of d attributes. So if d equals to 4, then there will be 2 power of 4. It means there will be like 16 possible combinations. Why? Yeah, you can see like, yeah, if I want to choose attribute 1 and attribute 2, or if I want to choose attribute 1 and attribute 3, or if I want to choose attribute 1 and attribute 4, or if I want to choose attribute 1, attribute 2, attribute 3. Okay, if I want to choose attribute 2 and attribute 3, so yeah, and so on. So there are many combinations, and there are possibly 16 combinations, and we can choose by using heuristic. What is the meaning by heuristic? We can choose using the significant test. Okay. So best single attribute under the attribute independence assumption. So we can use the significant test. Maybe if you want to use the chi-square test, it's possible. Or yeah, there are other kind of tests, the normality test or something. You can use that one to find the best attribute according to the test. Or we can use the best stepwise feature selection. It means when we have the best single attribute, then we pick first, and then the next best attribute condition will be selected next. Stepwise attribute elimination. So this is the reverse. Okay. So if we use the best stepwise, we can find the best single attribute and select the next attribute, select. But for the stepwise attribute elimination, we calculate all, and then we delete the worst attribute based on this significant test. Or yeah, you can combine the attribute selection and the elimination. So that's what called as the heuristic search in attribute selection. Or we can create, okay, we can create the feature or we can create the attribute. Okay. How we can create? So if we want to create, means we can just select the proper information so that the information or the data will be used more effectively. So the creation of this new attribute is very, there are many ways. Okay, so I just want to explain three kind of general methodologies. First, we can extract attribute. Okay. It's very domain specific. Okay, it means, yeah, it depends on your data. If your data is about sales, yeah, then yeah, you need to know about the sales. If your data about the income, yeah, customer confidence from income, then you need to understand how to determine that one. Okay. For example, I have this data: gender, income, and then I want to create a new attribute category. I thought that income is difficult to understand because it has a very big gap, for example. So I want to make the category. If the income is higher than 2,500, it is high. If it is lower than 2,500, it is low. Okay. So this is also one of the example for attribute creation. So if it is higher than 2,500, then it is high. If it is lower than 2,500, then it is low. Okay. We can map the data to new space. Okay. If we map the data into the new space, we can check based on the data reduction. We can use the Fourier transformation, or we can use the Wavelet transformation that we already learned. Okay. Or yeah, we can do the attribute construction. Okay. So the attribute construction means we can combine the features, and we can do also the data discretization. So this is also a type of data discretization. Okay. Combining features, for example, yeah, in Korea we also have like family name and first name. Okay. And we want to combine. We do not want to choose the data separately. So we want to use the full name. So yeah, we can just combine into full name, and we will use this data for our analysis. Okay, the second thing about the data reduction is the numerosity reduction. So I already explained to you, this is about the instance selection. So we want to reduce the instances to the smaller number. So reduce data volume by choosing alternative smaller forms of data representation. There are two kind of methods. The first is parametric methods. So we need to have the parameter, or the other is non-parametric methods. If we use the parametric methods, for example, regression, okay, yeah, we can assume that the data fits to some model and estimate the model, store only the parameters, and discard the data. Delete the data that is not necessary and accept the possible outliers. Okay. So there are some other models like log linear models. Okay, maybe I will not explain this one. Yeah, we can use how we can have the space and the dimension. And if we use the log linear model, we can just have some deletion on unimportant values. If we use the non-parametric methods, we do not use any models. So we just use like histogram, we just use like clustering, or we just use sampling. Okay, so we don't care about the model, we don't care about the regression, we don't need to do the analysis. Okay, I guess I will continue this thing in the next session. Okay, so I will stop